Welcome to Physics Made Easy channel. Last time we have done voltage gain for common emitter amplifier, and we have done with the phase relationship. If the AC input signal is like this, positive half cycle first and then negative half cycle, then the output signal will be like this. Output signal is 180-degree out of phase with the input signal. This is the important factor that we have to learn from the previous part, and we have discussed in detail how AC input voltage affects output VCE in both positive and negative half cycles. And now we shall take up very important factors. This what we have already discussed for NPN transistor. Same can be done for PNP transistors. Same explanation holds for PNP transistors. I will rush through this explanation, and these important part, these DC amplification factor, AC amplification factor, their calculations, transconductance, AC voltage gain and AC power gain, they are very much important from examination point of view. All the three or four kinds of examination, your board examination, your NEET examination, JEE main and JEE advanced, this particular calculation I will emphasize it, and we will also make a dummy calculation for it so that you can understand how to make calculations. And before that, the agenda for today's program is amplifier circuit showing PNP transistor. Now, in this case, input signal and output signal, they are out of phase. Common emitter amplifier, whether it is PNP transistor or it is NPN transistor, end result is the same. The last factor, and what is the end result? End result is that the phase. Now, this is P, this is N, and this is P again. Basics of circuit drawing are the same. This is emitter based section, it should be forward bias. For forward biasing, P should be attached with positive, N should be attached with negative, R is the resistance, C1 is the capacitance, this is the input AC signal. Biasing is maintained in such a way that this emitter base junction is always forward biased. This issue I have dealt in my previous lectures. Ri is input resistance, and at the same time Ro, RL, no sorry, there is no Ro, RL is the output resistance, and this is the battery. This section has to be reverse biased. Collector emitter section has to be reverse biased. In for that, this P is connected with negative of this battery, so to maintain the reverse bias. And now the next section, input wave is this and the output wave is totally out of form. If we proceed via the same logic, when input voltage rises, I will say VAC rises. When VAC rises, here we have got this negative. Forward bias decreases. VBE falls. If VBE falls, it means that IB falls. If IB falls, this implies IC falls. If IC falls now, then we have got this expression VCE is equal to VCC minus ICRL. This is the expression. Now, we were discussing this part. Now, IC decreases. If IC decreases, it means this VCE increases. Now, VCE is connected with negative of this. It means negative voltage increases. This part. So this negative voltage increases like this. And in the next part, this was for positive half cycle. Positive half cycle. Positive half cycle. For negative half cycle, here we will argue for negative half cycle. For negative half cycle, VAC will decrease. It falls, and now it will increase the forward bias. That will increase the base current. That will increase IC, and that will decrease VCE. Now, decrease in negative voltage means voltage is becoming positive like this. So what is important is output is out of phase by 180 degree. This is important. 180 degree out of phase with input. They are out of phase by 180 degree with input. So this is the basic relationship. Now, voltage gain or common emitter amplifier. This is common emitter amplifier and DC amplification is the first factor that we will discuss. DC amplification, this is the topic, DC amplification. Obviously, in this case, we won't take any change into consideration. So, remember, this beta DC, output is IC, input is IB. So it will be of the order of thousands, you can say. It will be of the order of 1000 because this is in milliampere and this is in micro. So the order of this beta DC, the value of beta DC is very high. First remember this thing. And now we have got this relationship beta DC is, first we have got here I, E is IB plus IC. So from here we will calculate IB. This is IB is IC divided by IB. This is IC divided by IE minus IC. Divide numerator and denominator by IE. So I have divided numerator and denominator by IE, and I got this relationship. IC by IE is alpha. Now it means beta DC is alpha divided by 1 minus alpha. And if you want to find alpha, and then that will be beta divided by 1 plus beta. We have got this kind of relationship. So if alpha is given, we can calculate the value of beta. If beta is given, we can calculate the value of alpha. Now, let us AC amplification. AC amplification, obviously, this is delta IC divided by delta IB. Now, which voltage is kept constant is collector voltage, VCE. This is kept constant. Now, it's a very easy problem, and calculations, numericals can be asked on the basis of this. For example, I want to calculate the value of this factor for a particular voltage. And let us fix that voltage. VCE constant can be any voltage. Let me fix this at 3. 3 VCE. Now I will calculate beta AC at what value? VCE is equal to 3. I will put this equal to 3. Let us, this is equal to, you can take 3. And I can choose any two intervals. Say I pick up this interval delta IB. First I will fix delta IB. Let I fix delta IB to be 50 microampere. This is 50 microampere. Corresponding value of delta IC. First is I will take it as 7. 7 milliampere minus, and then on this 100 it is 5 minus 5. So delta IC is 2 milliampere. Beta AC is equal to delta IC 2 milliampere divided by 50 microampere. Beta AC is 2 divided by 50. This is 10 raised to power minus 6 into 10 raised to power minus beta AC. This is 2000 divided by 50. This cancels and this is 4 and 0. This beta AC is of the order of 40. Its exact value is 40. Its exact value is 40. We can have different values of beta AC. This is at VCE. At VCE3 it is 40. At 5 it may not be 40. For example, here if you take this voltage at 5 and you again take this 100 volt, this is 3, approximately 4, and then at 150 it is approximately 5, 1 ampere. So here we will be having 1 milliampere, and here 1, and its value will fall to 20 beta AC. So the value of beta AC at 0.5 will approximately fall to 20, and at 3 it is 40. So its value keeps on changing. Next is transconductance. It is the ratio of change in collector current to the corresponding change in input voltage. So this is transconductance. It's a very important factor. How much output current depends upon input voltage. So we will write it like this. Gm, this is Gm is equal to delta IC divided by delta Vi, and this is equal to delta IC divided by delta IB into delta IB divided by delta Vi. This is Gm is equal to, this is delta IC divided by delta IB. This is beta AC. Beta AC. And now this delta Vi by Ohm's law, delta IB by delta Vi. This is input resistance. This is input resistance. So transconductance is equal to beta AC into input resistance. From here you can calculate even output resistance. Now the next factor is AC voltage gain. AC voltage gain. AC voltage gain AV is equal to delta VCE is the output voltage divided by delta Vi. This is delta IC into output voltage R0 divided by delta IB into input resistance Ri. This is output resistance. So this is resistance gain. Voltage gain AV is clearly equal to current gain. Current gain is beta AC multiplied by resistance gain. I will write it in full. Resistance gain. Beta AC is delta IC divided by delta IB. Now the next factor is power gain. Power gain. Power gain is change in output power divided by change in input power. So AC power gain is this. Change in output power is, you can say, delta IC square into R0 delta IB square into Ri. Obviously this is square of AC current gain multiplied by resistance gain shown by Rg. So we can also say that the power gain, AC power gain is beta AC into voltage gain. And the next factor that we will discuss is the frequency response. Question has been asked on frequency response. This is the frequency response, voltage gain, and here is the change in frequency of input voltage. And the graph is voltage gain rises initially with at smaller frequency, then it increases a plateau value. This is mid-range. At mid-range it is constant. At high frequency it falls like this. This graph is very important for amplifier. Amplifier is operated on this state portion. On this state portion it gives high fidelity. Mid-frequency range. In mid-frequency range amplifiers they are operated, or in this mid-frequency range they give high fidelity and their performance is good. With these words I finish this lecture, and the next part we will do in the next lecture. Only one topic is left in this marathon chapter. Thank you very much.